Hey, Eshan, are you there?
Hi, can you hear me?
I sure can. How's your morning going for you?
Pretty good.
Good, good. Well, Eshan, I was kind of wondering, the last class you're in, how's it do in that class?
Um, our semester hasn't ended just yet.
Okay,
I have one more test to go, and then after that, should be good.
okay. So where are you sitting at then?
So the last test, 28.5 out of 30. So now I just need at least a 95 on the next one to get an A in the class.
Man, you have definitely come a long ways there, haven't you?
Yeah,
How you feeling about that?
pretty good.
Good, good. All right. So you're back in the full swing of things. What have they talked about so far in your class?
So we did optimization
Hmm.
and then a couple other things over the past week.
Okay. Now,
Let me pull it
did
up.
you did you have certain questions on optimizations you're struggling to understand?
Not like specific questions, but just like optimization in general
Okay.
and word problems to do with that.
Okay. Now, besides the optimization, was there something else?
Um, like concavity and second derivatives and curve stick catching, but like that one's to me a lot easier than optimization.
Okay. What is it about the optimization you think that's challenging for you then?
I just find it like hard to like understand what to do in some places.
Is it because it's a word problem and it's not really giving you an equation?
Yeah, because like with related rates, I was able to understand like what equation I'm supposed to do, but like with this, it's just I'm confused sometimes.
Okay, that's interesting because related rates are also word problems. Um, what's the distinction then between those two to you?
Um, it's just like with related rates, I can feel like, oh, because this happens in like the real world, I can like more understand it better. But like here, like it's I don't know. I
I see.
feel like I need like a bit more like guided practice with those.
Okay. Yeah, not a problem. Okay, let's jump over here to the bit paper. Do you saw the link for it?
Wait, what'd you say?
Do you saw the link for the bit paper?
Yeah.
Okay, if not, I'll throw it in the chat box. All right, can you see right on the screen?
Hmm.
Perfect. All right, so when you're talking about optimization problems, talk to me a little about that. What is that? What are you trying to do in those kind of situations?
Um, trying to optimize the amount of like one or two variables.
Okay, when you're optimizing, you're trying to find, is it a maximum, minimum? Is it what's being played out?
Um, yeah, maximizing like something to do with that variable, I guess.
Right. So it's either user are given some kind of function or some kind of scenario, and you want to find like either the maximum or minimum. A lot of times it's going to have some kind of constraint it's going to be subject to.
Yeah.
Because if I'm looking at the maximum for a line, it's going to keep right on going, like in this example. But if I say I want to make sure it stops at a certain location, there's where my constraint comes in the play. And a lot of times in these problems, you're going to have something like that. You're going to kind of put it all together. Now, later on, when you take the multivariable section of this course, you learn a lot more about this optimization constraint kind of idea. But let's just kind of look at a problem to get the ball rolling here. So suppose a farmer has 500 feet of fencing material. You want to enclose a pasture for grazing. Now, the farmer only needs to include 3 sides of the pasture since it's being bounded by a river. Okay, so in addition, what he plans to do is do this by doing 2 adjacent corrals, so 2 different corrals, sorry, 2 different pens. Now, here's the first thing. Can you give a visual of what this is telling us? There's really no equation here, but let's see if we can actually pull one out. Okay, so first off, we know we have some kind of river, maybe just blue or whatnot. What kind of region are we enclosing?
Like a rectangle.
Presumably rectangles. Let's go do a rectangle. Okay. And altogether, you're going to have 500 feet of fencing material. Now, if I'm looking at this region, I can look at it from one perspective by looking at area, where I might want to maximize the enclosed area, in other words. So here, I just got to make a choice. Call this X, call that Y, and then the area is going to correspond to XY. But notice what this is saying right here, 500 feet. That's part of our constraint. See, we're going to have this region, then also we're going to take it and chop it up into 2 adjacent pins, these corrals. So imagine for a moment if you're the farmer and you're walking around. Start here and you go there. Then you got to go here. Then you got to go down here. What am I doing? I'm traveling along the
perimeter.
So I would have 3x y equals 500. That's my constraint. See, the line is constrained. It's no bigger than this 500. And my area is coming xy. So I have a multivariable function. And since we don't know anything about multivariable functions, at least not yet, it might be to our advantage to take what we have for a constraint and drop it in. So you can have a single variable function, and we can incorporate both of these ideas, these equations, into a single equation. Now, in this case, I'm going to have a quadratic. Does my quadratic open up or does it open down?
It opens down.
So it's going to look a bit like this. And if a quadratic, if your parabola, if it's opening down, you have a vertex. And that's going to correspond to the maximum point right there. Now, in this particular case, I don't really have to do any calculus to solve this problem because I know it's going to be a vertex. I know that if I look at negative b over 2a, I can take it, I can drop everything in. And then I know from here that this is going to correspond to my x coordinate that I'm going to need in order to hit that maximum value that I need. But since this is a calculus class, let's do a little bit of calculus here. So if I want to figure out the optimal solution, this is where I am going to be looking at derivatives. I would take my derivative, and then I would set it equal to 0 to find those critical values. And then I would solve for x. And there it is. So if that's my x value, I can find the y value fairly quickly. Now, again, this is going to be 250 over 3. Y. 3's go away. 250 for Y. And if I want to figure out the maximum area, hey, we'll just take it and multiply it out. And there it is. Okay, so let me pause for a second and ask you if you have any questions on this one.
No.
Okay. Well, let's take it and crank it up a little bit more then. Let me throw you this problem. So an open box is going to be made from a 16-inch by 30-inch piece of cardboard by cutting out the squares on the sides. Now, all these squares, we're going to assume we're going to have equal length. Here's the first thing you want to do again. Get a visual. That's the first step. Sketch it out. Don't worry about any of the equations. See if you can try to get an understanding what this is telling you. Then, from the picture, what you're going to do next is get the equations. You're going to extrapolate it however you need. Okay, so go ahead and play around with that for a moment. Okay, so you got your dimensions out. Now cut out the corners. There you go. Okay, so take it and conceptualize it. Pull it up. So you got this piece. What you want to do is think about how you're going to form that box now. This piece. Okay, talk to me about this variable right here, y. Why did you introduce y into the system?
Because I needed. Oh, I could just do 30 minus x.
Not x. Because there's an x on this side, also that side. 2x.
Oh, 30 minus 2x, yeah.
Mm-hmm. And likewise right here. That would be what?
30 minus 16 minus 2x.
You got it. Now, think about how that's going to correlate over here. Oh, there it is right there. Okay, good.
So then just
Now, I'm just kind of curious real fast. What are your bounds on X, by the way? Here's where constraint comes into play. Would it make sense for X to be less than 0?
no,
No. Would it make sense for X to be bigger than 8?
no.
No, because then we're going to have some problems, aren't we? Okay, so now you do have your function. How would you find the derivative of that? Do you remember?
Like I could use like product rule, or I could simplify it first and then use product rule.
Okay. You can definitely take it and expand out a little bit if you want to, then do product rule, your choice.
Yeah.
Okay, let me give you a moment there to see what you come up with. Okay. Now, let me pause you for a second here and see where you're going. I want to show you something that can speed this up a little bit. Remember the whole entire adage? We want to simplify these equations as we go. So notice right here, I can pull out a 2. Notice right here, I can pull out another 2. So my volume equation, I can take it and I can say it's going to be 4x, 15 minus x, 8 minus x. See how that's going to be a little bit easier to maneuver or manipulate than saying 30 times 100 or 30 times 16, then times 2. Makes it a little bit easier. So if you were to try to expand this one out, how fast could you do this one instead? And just,
That
we'll just leave the 4 on the outside. A whole lot faster, right? You get that? Okay. When you take it from here, and go ahead and take your derivative.
wait, yeah. All right.
Okay. Think about what you can do to make this a little easier, less complex.
Mm,
What's your gut reaction saying? Give a little hand here. See the four?
mm-hmm.
See the four?
Yeah.
See the zero?
Mm-hmm.
I would divide the four out. So if that four is not there, see how that was causing a little bit of trouble? It's kind of come out for sure because of I don't want to multiply it. But by dividing the four out, watch how fast you're gonna do it now. X squared and a 2 x squared makes it a 3x squared. Negative 23x minus 46x, 120. Okay, now let me pause for a second. I want you to see if you're seeing these things that I'm seeing here as I'm working through the problem to make it easier. Let's go back a
Yeah.
little bit. So remember what I did up here? I saw a common factor. I pulled out the 4 in a sense. And I know here in a moment, whenever I take the derivative, I'm going to set it equal to 0. And I know that 4 is not going to really amount to much in the overall grand scheme of things when I'm trying to figure out the critical values. It's going to divide out eventually. So instead of taking my problem and making it really big, let's simplify as we go, make it smaller so it's more manageable and we can speed through the calculations a lot faster. Okay, after we divide everything out, now it's a matter of factoring. How do you factor this? Now, again, I want to see if I can try to factor before I decide to invest a lot of time using the quadratic formula. Quadratic formula, it's a little bit slow. It's factoring is going to be a little bit faster. Okay, there's a 3x squared, so we do know there's going to be a 3x and x up here if we're going to factor it. Good. 10. Okay, perfect. So here we have x is going to be 10 over 3, or x is going to be 12.
Yeah.
Which one is it?
10/3.
Right, because of the constraint. Okay, now, Eshan, let's go back up to the problem again. See if you have a question about it. Remember, first thing is get a visual, and from the picture, see if you can get the equations.
Yeah.
All right. Ready for another one?
Mm-hmm.
Let's do it. Try this one. Okay, so take a moment, read it, get a visual, see if you can sketch it out.
Wait, no, it's the wrong way.
There you go. Okay, so you got your path, you have your location. But what's the path that's going to be the closest? Does that mean we're going to loop around like this? Or
No.
hook shot it around this way? What would it mean then? Bounce it?
I don't know.
The shortest path between 2 points in a plane is a straight line right there. So let's make this a little bit bigger so we can get a better feel of what's happening. Okay, I want you to see if that makes sense.
Yeah.
Okay, now you tell me what we're really trying to find. Okay,
The
so
distance of that line.
good. Let's call that D. Okay, now, Eshan, I want to find the distance for the line. Do I know some kind of formula that allows me to compute the distance between 2 points?
Um,
Pythagorean theorem. Good. And there's a nice formula associated with it. Remember what that was? Square root. Because you're really trying to find the hypotenuse. X coordinates, then Y coordinates. Now, one of we know is going to be 0, 2. The other one would be X and a Y. But if I'm on the curve, that means the Y value is the evaluation at the function value. Okay, so there it is. Take it and drop it in. We'll distribute. Okay, take it from there. Now, again, we're trying to find the optimal solution. So we got to find out our critical points. We're going to see what's going to happen with our D prime. Okay. All right, let me give you a moment there.
how did you get like this part?
Okay, so 0 minus X squared is,
X squared.
and then 2 minus Y, and Y is going to correspond to the part that's on the graph, which is this 4 minus X squared. So I take that, I plug that in, and I distribute the negative.
Ah, okay, okay.
Okay, let me give you a moment there to work through this from here. Okay, need to pause real fast. Tell me why you have a 2x.
Um, from the derivative.
That is the derivative of x squared, but is that really the function that I have? It's not. It's inside of a square root.
Yeah.
Composition. Except for composition, I have to apply the chain rule.
Yeah, I know.
Okay. Well, I'll let you go keep going then.
Is this it?
If you plug that in, does it make it 0?
Maybe it
Try
makes
it.
it undefined.
Okay, so that's possibility, I guess. When's it going to be 0?
Um, when it's equal to 1/2.
Look at the numerator. So if you have 1 plus 2, x squared minus 2, 0. So x equals plus or minus the square root of 3/2. Okay. All right. Let's go back up here, Eshan. Talk to me about the problem again. We have some kind of path we're looking at, and I got to find the closest path to it. That's going to indicate, again, I'm talking about a straight line. Okay. Now, I want to find the optimal solution here, but how challenging was this problem to you?
Pretty challenging.
Okay. Why was it pretty challenging?
I didn't know where to like start.
Okay. But after we got our graph, were you able to figure out from there, or was it still real challenging?
Still pretty challenging.
Okay. Why was it challenging after you knew the plot and got your function?
After I got my function, it wasn't as bad. It was just algebra, but like,
Okay. Now, here we got our distance formula. Was that pretty challenging with the square root?
yeah.
Took some time, didn't it? Now, when I'm looking at this given problem, what I want to do is I want to find the closest path, or the closest distance from the point to the line. And we do get our line up here. And we do have our equation. We do have our distance formula. We have our distance between 2 points, x0, x1. Now, would it surprise you if I told you you can actually do this problem in about 1 to 2 minutes? See, over here, it's a big time sink. And this kind of problem, you see this a lot on exams, especially when you start getting into like an honors kind of a course. This is really testing to see if someone understands the ideas and if they can see something to speed it up. You know what the secret is? How can I make this go faster? Well, notice what we're doing. We're trying to maximize or minimize this function call. Look at the radicand, the piece under the square root. See how it's always going to be positive? You have positive value, so you have positive value to another positive. You're never going to get negative, are you?
No.
So here's the deal. If I want to maximize or minimize the square root, it's going to correspond, the maximum minimum is if I look at this and I square it. Now, Eshan, what's the benefit of squaring the equation? There's no square root. I don't have to worry about this piece that goes down below, composition, the derivative. Look to see where I have where it doesn't exist and see what happens. I don't want to have any of that, because when I look at the actual function itself, x equals 1, it is going to correspond to a critical value. I'm looking at my d prime, but it's defined for the function anyway. So I can kind of see that, yeah, that's probably not going to be too much of a big player here in this problem. And if I took everything and then if I plugged it in from here, once again, I would have 0 minus 2 quantity squared. And then I would have the x squared minus 2, because remember it's 2 minus 4. And instead of saying d squared, I'm just going to shake it up a little bit and say f of x, just to get away from here. So here's what we do. In this kind of problem, what we want to do is we minimize the sum of squares. That right there, that's the secret of how to do this problem very quickly. So you minimize the sum of squares by taking the square root, popping it off, and look at that. It's a sum of squares. Now, from here, we can then start evaluating. We can expand out a little bit. We would get our x to the fourth minus 3x squared plus 4. Which one would you rather take the derivative of? The square root or the polynomial? I would do the polynomial all day long.
Oh, yeah, probably.
Because bang, I'm done. See, over here, you're still kind of working on the composition. And while another student's going through this, you know the secrets and you're going to speed through this as fast as you possibly can. Give yourself the competitive advantage. Shave precious minutes off your exam. X equals 0. But that doesn't make much sense here in this case. That's not really too valid. The one that's really valid is this one. And look what we get. It's the exact same thing, isn't it?
Yeah.
So it's a lot less work. You get to the answer a whole lot faster. Now, what I want you to do is write down your notes. Write down this trick, because I'm not sure if they're going to teach you this in class. If you want to minimize the square root function, try looking at minimizing the radicand. Or if you want to maximize it, then look at the radicand as well. If you do that, you can see how it's going to be a time saver for you.
Mm-hmm.
Okay, so let me give you a moment there and let you synthesize that and see if it really resonates.
Yeah.
Good. Okay, I want to throw this problem your way. I want you to kind of model again what I just did. Yes, you could possibly do it the way we just did it, but let's see if you can do it by minimizing the squares. Adjust your graph. 5 zeros over here. Good. You got your visual. You're locking your thoughts down. You have your visual. Good. Okay. Get your distance formula. Now, once again, you are looking at a point here, and points here are known as x. And what's the y value on the square root mean? It means square root of x. See the y value?
Yeah.
Okay. Give it a little hand here. Go ahead and fill in the details. Oh, not zero, not zero. Because you're going to the point.
Yeah.
The point's x.
So for this case, it would just be 5 squared.
No. You're going from here to there. The x value is 5. The x value up here is x. Because you don't really know what it is. I mean, it's more like this in terms of your plot. This plot, you could confuse yourself thinking maybe it is 5, but it's going to be x, y, and this is 5, 0. So x and 5. See how that works?
Mm-hmm.
Okay, what about the y did?
Um,
The y value on top is called good. And the y value at the other point is called, there it is. Okay, now, Sean, take that radicand and simplify it. Maybe square that out. If I can double check that. There it is. And this piece back here. Good. Okay, let's simplify it down one more time. Combine our like terms. And there it is. Okay, now, once again, this is the stage where a lot of students are going to start burning up a lot of time because they're looking at the D and they're saying, okay, I got to minimize, maximize that function, which is true, you do, but you can circumvent the complexities of this by looking at, what did we say a second ago? It was
square root.
we minimize the sum of squares right here. So to minimize the distance, we minimize sums of squares. Okay, make sure you write that down. So to minimize the distance, minimize the sum of squares. Okay. That's a nice trick, but they don't always teach in this class. So what you want to do now is minimize the radicand, in other words. Go ahead and minimize that radicand. Where's the minimum at? Or the maximum at?
Um,
Take your derivative.
oh, yeah.
No two on top. There you go. And then take your derivative equal to 0. Good. Wow. There it is. So right here, about 9.5. That's going to be the closest to the 5, 0. Eshan, how you feeling about that one?
Good. So can I just like disregard the square root on these problems?
You most certainly can. But I want you to see if it makes sense why you can do that.
Kind of.
Okay. If I want to minimize or maximize my function, I minimize or maximize my input of the function, the sum of squares. Now, it might take a little bit of time for you to really comprehend that. That's why I want you to write these notes down so you can come back to it later on today in an hour or two and later this evening. Say, okay, what did he say by that? You go, okay, minimize, maximize the function by maximizing the sum of squares idea. That way it's going to start resonating a little bit more.
Okay, yeah.
Okay. See if you can get a visual here in this problem. Okay. Good. Now, let me pause you for a second. When it says it's between the two towers, does that mean it's halfway between?
No.
No, we don't know. Good. Okay, now I'm gonna throw another term out here for you. So in case you see it, it's called a guy wire. Do you know what those things are?
I've heard of it.
Okay, so you see this all the time. You see some kind of tower, like antenna tower or whatnot. And if you look off the distance, you'll see wires.
Oh, yeah, to hold it down.
That's exactly what this is. So we have two towers, and it's really talking about like some kind of maybe potentially a guy wire right here. Because that's just all that means. Okay, so you got a pretty good visual right now. And we don't know if that's X and X. We don't know if it's half and half again. So maybe like
Oh,
X and Y.
I meant like a Y over there. That second one. I just made it look kind of like an X.
Oh, okay. Make the second one a Y then. You have a constraint there, don't you?
Mm-hmm.
Perfect. Okay. What do we need to do here in this problem?
Um, we want to minimize the length of wire we need. The length of wire we need is like
What is it? What does it mean to minimize length of wire? What is that? What's length of wire mean here in this context?
the total length of these two.
Good. What's Y again?
Um,
It's right there.
yeah. So we could take out Y with that.
Okay, so is that a V right there or
That
W?
W. Yeah.
Okay, we'll go with your notation. Alrighty, Sean. So I got to find the minimum now. I got a interesting function. What am I ever going to do?
Um, is it possible to take the derivative of either one of these inside pieces? Or do we have to simplify it?
I would kind of simplify it maybe a little bit in here if you need to. Now, here's kind of the deal. If you can figure out a way to minimize this piece while at the same time minimizing this piece, then you could take the two equations and blend them together. Now, in this particular case, let's just kind of work it with the square root here. And I'll let you explore it later on. I'm going to call it d prime just to keep with what we're doing earlier. Here's
If
going
I
to be our value. Go ahead.
real quick, if I, for example, just minimize this individual piece right here,
Mm-hmm.
wouldn't the x value also be the maximum of this piece?
Okay, go ahead and minimize that for a second. If you look at the x squared plus 28 squared, if you yank that part out, take the derivative, and derivative for a constant is called 0. Set equal to 0. That'd tell you the next would have to equal
0.
Okay. Would that make sense then? We have our two towers. We had our y, we had our x. So what that means is take the line and drop it straight down and just connect up like that.
Yeah. So
Would
that
it
would
make,
also be the maximum of this other function.
that wouldn't make much sense though, would it?
Yeah.
It's got to be between it. That's not between. So I can't do that here in this case. Now, you can also, or do you have a calculator nearby?
Um, yeah.
Okay, remember there is that solve feature on your calculator. There's also that the derivative. So if you solve this, it's probably more like a calculator-based problem. But you do want to set equal to 0. And then you do want to solve. We'll get this if you were to set equal to 0. Now, here's the real question I got. How would you find x here in this case?
You divide the other side by like square root of 1049.
Mm-hmm. You can definitely expand out if you wanted to, square everything, try to recollect it all, and hope for the best. It seems a little complicated though, doesn't it?
Mm-hmm.
Okay, so in this problem, one thing you can do is use the graphing feature where you have y1 and y2, top left-hand corner. You can plug this in for y1. You plug this one into y2, graph it out, and see where the two graphs intersect. We zoom in real close here. It's about 25.6.
Mm-hmm.
Okay. Now, see if all that's making sense to you, how we're putting this together.
Yeah.
Okay. Any questions on it?
Not yet.
Okay. Well, let me drop you a few problems. I want you to think about these later on here today. Okay, here's one right here. And here's kind of a challenging problem. Okay, so I want you to really think about number 10. Get a visual with it and see what you can get. Now, work on this one later on today. And if you feel like you got it, go ahead and put your solution up here on the bit paper. We'll take a look at it next time. And I'll take a little sneak peek of it later on today. Just send me a quick text message and I'll take a look at it. But I really want you to see if you can try number 10. Now, you're going to have to get a visual. And you're going to have to see how things are played out. Here's kind of a quick little hint. Okay, so you're going to be traveling on land, also potentially on a river. You're just not for sure when you're going to veer off the land and go into the river. Okay, there's your hint. All right, Eshan, how you feeling about the optimization now? You feeling a little better about it?
Yeah.
Okay. Do you have any other questions or any other things you want to talk about before we close up for today?
Would it be possible for us to meet on Wednesday as well?
You have a test coming up on Thursday?
On Friday.
On Friday? Sure. Let me see what I have. So instead of meeting next Saturday, we're going to meet up maybe on Wednesday, you said?
Yeah.
Okay. What times can you meet up on Wednesday this term?
Um, Around the same times, anything past like 2:30 CST.
Okay. I have a class that gets out about 3 o'clock-ish. So let's go ahead and set it for Wednesday about 3 p.m. Central. And if I'm running a little bit behind, I'll let you know.
Okay, yeah, sure.
Okay, so instead of meeting on Saturday, I got to meet for Wednesday for the 17th.
Okay, yeah, thank you.
All right. Well, Eshan, it's great talking with you again. Keep up the good work. We're going to try to get that 95, if not a little bit higher, so you can definitely get your A in your class.
Okay, yeah.
All right. Well, I'll talk with you on Wednesday.
You too.
All right. Take care.
You too.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.